So welcome everyone back to after our little summer break to the first Fridays of this new season, and we actually have two presentations that are sort of paired together. The first one will be by Professor Jim Woodhouse on the his modeling of the soundpost, and then we're going to follow up next month. Joseph and Luca will present the results of the experiments that they did during our acoustics workshop in June. So, Jim, take it away.
Right, and people who are not muted might mute themselves because it always causes echoes after a bit. Right, let's see if I can show some slides and it remembers those things. Okay. So the last time I did one of these talks, it was about the bridge, I suppose about a year ago. And that was prompted by Joseph wanting to know more about bridge adjustment. So we did some work on that. And really just by association of ideas, it seemed logical to me that having thought a bit about the bridge, I should think about the soundpost. So this, for what it's worth, is the fruit of that thinking about the soundpost. I don't really need to tell you guys what a soundpost is, but I like this image a lot. So look how crooked it is. And that's a famous one. Now, in the bridge work, the stuff that I was able to do and then the workshop was able to pick up on came fairly close to relating to workshop practice. In the end, we could take a real violin body without the bridge, do a few measurements on it, and then do a kind of virtual bridge fitting in the computer and see and listen to the effect of bridge adjustments. The soundpost is more complicated, so the talk just begins with a little bit of warning. It's for reasons that I'll explain towards the end of the talk. It's not so easy to do a completely equivalent thing with the soundpost. I will do something based around a real instrument and some measurements, but the purpose of this talk is more to understand what the physics might be behind the soundpost, and understanding may give you some ideas, but there is no claim here that you can straight away transfer this stuff into the workshop. So let's start with the easy stuff. What's the soundpost for? Before we start doing subtle adjustments, why do we have it in at all? And of course, the soundpost has a role in stopping the top collapsing under the load from the bridge, but disregarding that, the main acoustical function of the soundpost, I'm sure most of you know this really, is that if the violin was as symmetrical inside as it looks from the outside, then it wouldn't make a lot of low frequency sound. And the reason is in these couple of sketches here. So here's a violin with no bridge and no soundpost, a completely symmetrical body. Here's the bridge. The vibrating strings apply forces at the top of the bridge, which are basically in this transverse direction. So what those tend to make the bridge do is rock. And so it pushes down on one foot and up on the other pretty much equally. And in schematic cartoon form, you might think that the top would then vibrate in the kind of way that's shown in this red line, which is exactly as much up on one side as it is down on the other side. So there is no net change of volume. Now, change of volume is what you need to radiate sound at low frequencies, long wavelengths. When the wavelength of sound is long compared with the size of the instrument, which it is certainly in first position on the G string, then if the top vibrates like this, the air simply sloshes backwards and forwards because the volumes match. There's no need to compress the air and make pressure waves in it. You just get some local stirring. You put in a soundpost, and the bass bar contributes as well, but especially the soundpost. And the simplest way to think about that is the soundpost creates a hard point on the top, more or less under the 1 foot of the bridge. So you apply the same transverse force from the string. The bridge still rocks, but instead of rocking about the middle of the top, it tends to rock around the soundpost. So it still goes up on one side and down on the other side, but now it's not symmetrical anymore. So the bit going up on the left is bigger than the bit going down on the right. There is then a net change of volume, and that leads to much stronger sound radiation at the very lowest frequencies. Now we'll see some plots of this, and we'll hear an example of it in a moment. This only applies up to 800 hertz, 600 hertz, something like that. But it's a really important effect. So here is, now I'll explain later on how this plot is generated. This is a frequency response done in the usual way. A hammer tap on the bridge at the G string corner in the direction of bowing, measuring with a microphone. And it was in a somewhat reverberant room. That's why the plot is so fuzzy up here. The red plot is an instrument with a soundpost in. The green one is the same instrument with the soundpost removed. And above about 800, 700 hertz, they're pretty much the same. But at the low frequencies, the green one is way below 10, 15, 20 dBs below the red one. I'll explain later on how this plot was done. I described it as a measurement, but as you will all know perfectly well, the red curve can be a measurement, but the green curve, it's not, well, you wouldn't want to take an instrument you valued and take the soundpost out with the bridge and the full string tension still on it. So this is a semi-synthesized measurement, which I'll explain right at the end. But that's not really what we're most interested in, taking the soundpost out altogether. Yes, it will have a drastic effect, so we'll hear it in a minute. But what you spend your time doing with soundpost adjustment is doing small things to it. And people have this belief that that makes a very sensitive difference. Probably that belief is justified. It's the stock in trade of those tone adjustment specialists. So that's what the talk is about, trying to understand something. So something I was told, experts, it says vaguely, specifically the expert was Robin Aitchison. I don't know if he's in the audience today. And when he talked about soundpost, he said we think about three things: tightness, position, and fit, in that order. Now, from a physics perspective, position and fit seem perfectly clear, but why does tightness do anything? And what does it do at all? And then why should it have a sensitive influence? And what we'll see in a minute is that these things are not as different as you might think. There are connections between all three of those things. And I think that probably contains the real reason why tightness is important. So I think you can see what this is. So here's a schematic cross section. This slopey bit is sliced through the top, and here's the end of a soundpost, and it might be fitting snugly or it might be way out like this. But it's not as simple as that. The thing that looks as if it's fitting snugly, if we were to put it under a microscope, the two surfaces are not perfectly flat and perfectly mated. And in, again, a cartoon form, both surfaces, the inside of the top and the end of the post, have got little lumps and bumps, which in the technical jargon are called asperities. They might be to do with wood grain, they might be to do with tool marks from how you carved the thing. But one way or another, the surface, when you look closely at it, is not really flat. And that's going to be really important. Now, how does the soundpost communicate with the top? Well, basically, it could do two things. It can supply an axial force. So I've separated them and then got blue arrows here for the forces. So there could be a upwards and downwards force. And it might also transmit a bending moment, at least if it's like the left-hand post and not the right-hand one. In terms of modeling, we can model the effect of these asperities, rough surface, on the axial force component of what's transmitted, can be represented simply by a spring, one on the top and one on the back. The similar effect, and we'll talk about the stiffness of those strings. Those springs are to do with the squashiness of these asperities that are in contact. The bending moment transmission means that you can also think of torsion springs at the end. The torsion spring is like what you used to have in a watch back in the days when you wound them up, for those who are old enough to remember things that didn't have batteries in. So the kind of model we can use is an axial rod with some axial springs and a bending rod with some torsion springs, connecting the two ends to the instrument body. If you fit the post tighter, you squash the asperities a bit more. That means that the actual area of contact, so as I've drawn it here, this is a rather loose post. There's really only contact here at a few rather small points. That means the interface is rather squashy, and that we would represent by a rather weak spring. If you fit the post tighter, you ram the two surfaces together a little harder, the contact area grows a little, and that means that this contact stiffness is stiffer. How stiff? Well, here's one way to think about that, although after I've talked through these slides, I'll say, actually, this doesn't matter very much. If you think of putting the post not in an instrument, but between the jaws of a metal vise, so it's essentially rigid, then if we just think about the axial stuff, well, the post has axial resonances, and then it's supported between these hard surfaces by these two contact springs. And if you change the stiffness of the springs, they're both the same, just for simplicity here, all those resonance frequencies of the post change. So this is the resonant frequency as a function of the stiffness. Have I got that the right way? Yeah, that is the right way around. This is quite a wide frequency range. This is for a typical dimensions of a spruce violin soundpost. And what you see is that if the spring stiffness is really weak, so super loose post, then in the end, the first resonance goes all the way down to 0. or more or less zeros, and that simply represents the post bouncing between these not very stiff springs, not deforming at all, just as a mass between the springs. You tighten the springs up and the frequency goes up, but it doesn't continue going up. If the stiffness gets high enough, then the end might as well be fixed. And so that puts an upper limit to how high that frequency can go. It's quite a high upper limit. As you can see here, it's above 25 kilohertz, but that's by the by. There are higher resonances, but that we're well outside the human hearing range here. The bending resonances with their torsion spring have a rather similar behavior. The post has bending resonances, and then they're restrained by these torsion springs against the hard surfaces. And you get a similar kind of thing where the frequencies go up as you make the springs stiffer. But now the lowest one doesn't go all the way down to zero. If with a super loose post sitting on one edge, it's still carrying the axial load, but the torsional stiffness has gone to zero. But the post, well, we're assuming the post doesn't fall down now, but it's as if there was a hinge at both ends. And so the post can still vibrate in bending ways, and it vibrates like a bar, a beam with hinged ends. As you make the post tighter and tighter, so this torsion spring gets stiffer and stiffer, the frequency goes up, less dramatically than they did for the axial resonances. But again, they reach a limit, because once the spring stiffness is high enough, the post might as well be glued into place. And the ends, instead of feeling as if they're hinged, feel as if they're clamped in place. Now, in both of these plots, the only real relevance of this is that this is one possible way to try to find out what this contact stiffness ought to be. And the dotted line across the middle of these two graphs is my estimate for a typical stiffness for a typically tight but not stupidly tight post, realistically tight. And I did this by actually putting a post in a vise and then tightening the vise up. Now, in a vise, of course, you can apply way more force than a violin body is capable of resisting, or that you would want to do. So the actual stiffness puts it rather in the middle of this range where the frequencies are varying. However, probably those post resonances are not in themselves very important in the complete instrument. If I just go back to the slide here, the axial ones are really rather high. The bending ones are there, but they don't communicate with the top in a very interesting way. So probably they're not directly important, but there is a more subtle effect, which I think is probably a lot more important. And so we go back to this picture with this apparently well-fitted post, but we zoom in on it and we see these asperities here. Now, think what happens if you put your setter in and you push this post a little bit. So you move the top of the post maybe 1/4 millimeter sideways. Some small enough amount that it still looks as if it fits. Well, it looks as if it fits, but you have done something. So there's no visible gap, but by putting this very small tilt into it, you've made one end press against the top harder than the other end does. And that means that schematically, our contact springs have a gradient across the spring is rather weak at the loose edge and much stronger at the tight edge. And that has a consequence. You can't see this, it still looks like a post that fits. But because these springs get much stronger towards one edge, it means that the effective position, the middle of this stiff spring, where the post, where the top feels that the post is touching, is biased towards the stiff side. So the result of that is that you do a tiny physical shift to the one end of the post, creating this tiny tilt. It looks as if it's still fitting, but you might only have moved the end of the post by 1/4 of a millimeter, but you might have shifted the effective position by a significant fraction of the diameter of the post. So instead of being 1/4 of a millimeter, you might have shifted the effective position by 3 millimeters. Or, you know, as you tilt from one side to the other, you could go across the full diameter of the post. So small differences in tilt create effective shifts in a much bigger than the one you can see when you peer in through the hole. So we want to explore that a bit. Now, this is where we can't do what we did with the bridge. In the bridge equivalent study, I went straight to a real violin, but a computer model of the bridge. We can't do that for all the questions we would like to ask, and I'll explain why in a little bit. So I'm going to do some computer studies just to get a feel for what might happen with various types of bridge soundpost adjustment. But instead of a real violin, we're going to have a scarbox violin. We're going to have rectangular flat plates. They can be roughly the right area and made of the right material. So we've got a rectangular spruce top and a rectangular maple back with about the right area. So they've got vibration modes in roughly the right sort of place. The ribs, just for convenience, are rigid. But I will use quite a detailed and accurate model for the soundpost and in due course for the bridge. I've put the footprint of the bridge feet here, but didn't try to draw the bridge on the diagram. Now, you may think that's got nothing at all to do with real violins, but of course there are instruments that are not so different from this. This is a Sabar trapezoid violin in some museum in France. And I'm told that these things can actually sound quite good if they're well made and well set up. So maybe there's some hope for this simple model. But if you don't believe it, I will get to real violins by the end of the talk. The virtue of the cigar box is that we can get a really simple model in the computer. Rectangular plates have vibration modes, which every undergraduate learns in about their second year. So the mode shapes and the frequencies can be predicted, and how they vary if you change the parameters can be predicted. So we can use the model to explore things. So here are two comparisons. On the left is the bridge admittance with a theoretical bridge, where everything is theoretical here. The red curve is with the post in, the blue curve is with no post at all. And probably your first impression of this is that they're really remarkably similar. So removing the post altogether has not made all that much difference to the bridge admittance. There are places where there are 10 dBs different, but not all that different. But on the right, we have the radiated sound, and that's the other virtue in using rectangular plates, is that we can actually compute an estimate of the sound radiation from our cigar box. And now, again, the red one is with the post in, the blue one is without the post. At higher frequencies, they rather broadly similar, but at low frequencies, they're very different for the reason that I explained at the beginning. The one without the post is symmetrical and is a lousy radiator of sound at very low frequencies. And I think there are now going to be 2 sound demos. Now, everything here is theoretical, except the violin playing. So I'm going to play a couple of demos done in a method you've probably heard of before, where we take a recording of the string force from a real violinist, but then we use that with a process called convolution. We do something magic in the computer, and we can synthesize the sound of the instrument. So you're going to hear first the red curve and then the blue curve. Now, unless your audio is really lousy, those should have sounded strikingly different. The first one, reassuringly, does sound quite like a violin, I think, given that it's actually a rectangular cigar box. And if you've ever done the experiment of playing a violin with the soundpost out, and if you want to do that, the trick, by the way, is to slacken off the top 3 strings and just leave the G string under tension. And a violin body can perfectly well stand the tension of 1 string. And it's something I do as a lecture demonstration. You can have someone playing in first position on the G string and then come up over their shoulder with a soundpost setter and knock the post out. And the change of sound is really rather similar to what you've just heard. So that's encouraging. But again, that's not really what we're interested in. Removing the post altogether is more drastic than anything we want to do. We want to know things about adjustment. And this is where the cigar box model has the payoff. We can simulate all the kinds of adjustment that we're interested in without any expensive woodwork and without any risks of things collapsing. So first of all, what I'm doing here is varying the stiffness of those axial contact springs. So the black curve here is my best estimate of a realistic stiffness. The red curve is a very low stiffness of a loose post. And the blue curve is a very high stiffness, so it's essentially a post that's glued in place with these some epoxy in place of those asperity contacts. And what you can see is that the red curve is quite different, with the loose post down here in the signature mode region. There's a significant effect on the body mode frequencies. Well, this is only the cigar box. It hasn't got realistic signature modes, but the qualitative effect, I'm sure, would be the same in a real instrument. But at high frequencies, there are differences of 5 to 10 dBs. They're easy to believe, I think, that there might be audible differences here. The black curve and the blue curve are never all that different, but they get to be about 3 dBs different in places. So that's adjusting that axial contact stiffness. If we adjust that torsion spring stiffness, now it's the same color code. The black one, which you can hardly see, is the best estimate of the real thing. The blue one is so high that it might as well be rigid. The red one is actually so low that it might as well be 0. And I had to plot the red curve here in dashes because most of the, over a lot of the plot, it actually covers up the black curve. What you see here is not very much. This torsion stiffness is not creating big effects in the way that the axial stiffness did do. So this strongly suggests that the axial stiffness is far more important than the torsional stiffness. I was surprised when I first found out that, because the most obvious, on the face of it, obvious physical effect that might be affected by post fit and tightness is precisely this torsional stiffness. But it doesn't make any difference to the sound of the violin. But the axial stiffness looks as if it might be significant. We will take advantage of this when we come to do modeling. I will take the liberty of looking at this right-hand plot and saying, we'll just disregard the torsional stiffness. So when we come to fitting a virtual soundpost in a real violin, I will only actually try to fit the axial stiffness. But now in the cigar box model, we can simulate the kind of adjustments that you're interested in. Moving the post around, that's the thing you most want to know about. Now, in the typical spirit of physicists, I've done rather big movements here. So this is this is the bridge footprints. These are 3 positions of the post separated in the east-west direction. And then when we come to look at this one, the same thing in the north-south direction. And I've moved it, the center of the post, by 5 millimeters. Now, remember what I said earlier, you may think that you never move a post anywhere near as far as that. Well, you might be wrong. You might be moving it effectively by 3 millimeters when you tilt the post a little bit. But mainly I did it so that we can get nice big effects that we can see. The color code in the plots goes with this little cartoon here. So the regular position is the black curve, westwards is the blue one, eastwards is the red one. And they're not wildly different, but there are significant differences here. There are places here where all 3 curves are spread out about by, look at the scale on the left, 3, 4, 5 millimeter dBs. So it looks as if there might be significant effects here. Whereas the north-south ones, there are places where there are differences, but over a lot of the frequency range, this adjustment seems to be making remarkably little difference. So it looks as if in the cigar box, in this idealized world, east-west movements are more sensitive than north-south movements. Now, you will want to know, can we hear it? Are these effects important? So let's just go back to here. Now, the one I'm going to do, I'm going to illustrate something with the shift from the black to the blue, 5 millimeters westwards. No, does it say 5 millimeters? Not true. 5 millimeters eastwards, the black to the red is the particular case that I'm going to illustrate. So what we can do is we can do the convolution trick that I just demonstrated in that sound example earlier. So we take a piece of real violin playing and we can run it through our model with the post in the 2 different positions. We can take each of those and we can generate, this is essentially a spectrogram, frequency along here and time up here. Actually, for experts, this is something a bit more technical than a spectrogram. This is a time frequency plot, but it's using, rather than just using FFTs with constant bandwidth, it's using filters that approximately match the filters that you've got in your inner ear. So it's something kind of excitation pattern on your basilar membrane. So this is a kind of perceptually relevant spectrogram. I always plot them this way around with frequency on the horizontal and time on the vertical. And it's the same snatch of Tchaikovsky that you heard earlier. So that's one or other of the cases. We can do that with both before and after the shift, and we can subtract one from the other and subtract the decibels. This is a plot for this particular example of the difference in dBs in this plot. And the scale runs all the way from -20 to +20. There are places where the shifted one is louder, positive dBs, yellow. There are places where it's quieter, tending towards the black. Now, if we want to generate a single plot that we can visualize, we can take each frequency and we can just take the average, decibel average along each frequency, and then we get something we could plot as a graph. So this is the dB average, same frequency scale as here, for a 5mm shift of eastwards of the post in our cigar box. So this is the decibel average based on real music and on something that's vaguely perceptually relevant. And there are wiggles up and down. In particular, there's one peak for, so just around about 3 kilohertz. The shifted one is actually 6 dBs louder on average. So that's this yellow stripe here coming through strongly in the average. So fix in mind what that plot is. That's showing the effect as a function of frequency of a particular shift of the soundpost. Now, if we gather those together, we can do the same thing for shifts in different directions. And I've got all 8 of the compass points here. So the one we've just looked at is the one with the red arrow here, the eastward shift, that's that big peak. And here is going around the compass, south, southeast, east, northeast, and so on. So the ones that are north, southeast, and west are the 4 that we have in these 2 plots that are the same as we saw earlier, but I've put the in between the 45-degree diagonal directions as well. And this is showing the kind of thing that you would expect. All right, this is a large post shift, but in this averaged sense, they all get up to a few dBs, and the pattern is different for every position. So shifting soundpost in different directions makes differences big enough to be audible, and they're different for different positions. I don't think anyone in this audience will dispute that. That's the answer you expected. Say again, this is still only for the cigar box, but qualitatively, this seems quite encouraging. So now, finally, cigar boxes are all very well. Can we do something with a real violin body? Well, I'm going to demonstrate something, but here is the snag. So phase 1, I'm just going to do a virtual post fitting. And then in stage 2, later on, we'll do the post and the bridge. In order to fit the post, now this is the point where I'm going to take advantage of that discovery from earlier that the torsion springs really don't matter. I only need to think about the axial effect of the soundpost. And of course, I don't know what I know the post details. I know what it's made of. I know its dimensions and its weight. So I've got a perfectly good model of that. But I really can't guess what these contact spring stiffnesses are. But the post, if we're only looking at axial motion, the post only touches the box at 2 points, one on the top and one on the back, of course. So to do a virtual fitting, what you need to do, so you take off the bridge and the strings, and you take the post out. So with just the empty body with no post, and I do a vibration measurement, a set of vibration measurements involving these 2 points. So that's 4 measurements. I tap with the hammer on the top, and I measure both on the top and the back Then I tap with the hammer on the back and I measure on the top and the back. So there are 4 measurements on the box. And that is enough then in the computer to add a theoretical model of the soundpost at that particular position. Now, this is the reason that in order to look at post movement, I had to use the cigar box. I can do if I decide ahead of time where the post is going to be, then I have to do my measurements on the body in those 2 particular positions. If I want to know what the same post will do if it's shifted, I need to do more measurements. And every place you want to investigate, you'd need another measurement. And that rapidly gets very laborious. So I just did 1 position. So I do these 4 measurements without the bridge and the strings, measure the admittance at the post. There are 2 stages. Right. I should have said this. So we take off the bridge and the strings, but before we take the post out, we do this driving point measurement at this top position. So that's the actual effect on this violin body of having its post in. That'll be our standard of comparison. We now take the post out, do the 4 measurements that I just talked about, then we fit a virtual post in the computer with some value of the contact stiffness, and we ask, does it fit the real thing or not? So just look at the red curve for the moment. I'll tell you about the blue one in a moment. This, I can do this virtual fitting with lots of different values of this contact stiffness, because I don't know what it is. And in each case, I compute the admittance at the post top, and I compare that with the measurement that I did before I took the post out. And this is the RMS difference in dBs between those as a function of the post stiffness. And very reassuringly, it has a clear minimum here. And that is our prediction for what the actual contact stiffness for that post in that position. Just a bit bigger than 1 on this scale, whatever these units are here. So, and again, I stick with the red curve for the moment. When I take this best fitted position, here's what I get for that admittance on the top. Now, which way, where is it? And the black one is the measurement on the real violin with its post in. The red one is the reconstructed version with my best estimate of the post stiffness. Those are similar, they're not identical, but I look at the dotted curve in the background here. That's the same admittance on the same violin body with the post out. So fitting the post has taken the dotted curve all the way down to the solid black curve. And then my computer model, based on these measurements without the post, has done a pretty good job of reproducing that. I thought this was good. So I did that measurement. So my sacrificial violin that I usually use for these measurements, in whatever state it was in. So I measured it with its, I took the bridge and the strings off, I measured it with its post in, I knocked the post out and did the other measurements. But when I knocked the post out, I discovered that the post was looser than I would have wished. So when I put the post back in, I fitted it a little tighter. And then I repeated the measurement with the tighter post. And finally, that's the blue curve. So I just did the whole, it's the same, the body without the post, those measurements are all the same. But now I'm comparing with a measurement of the violin with a tighter post rather than with a looser post. And again, we get a curve with a minimum. it's much flatter and it's way stiffer. So we were 1 point something megawatts it's per thing, and it's now 4-ish, 5-ish megawatts it's per thing. So that's the predicted effect. Fitting the post tighter makes these contact springs stiffer, and that makes a difference to things. So that was an inadvertent experiment. I had no idea the post was loose until I got into this state and knocked it out. So that's encouraging. That's fitting a sound post in the computer. And just remind you, this model, which has done a fairly decent job here, is completely disregarding the torsional stiffness. This is only allowing for the axial effect of the sound post, and that seems to do a pretty good job. So finally, can we do the whole thing? Can we do the whole setup in the computer? Bridge and sound post. Well, we can, but it's a very laborious measurement. So there are now, there are 4 points on the body that are now interesting. The 2 ends of the post that we had before, and the 2 bridge foot positions. In order to do a virtual bridge and sound post fitting, what we need to do is take this violin, take off the bridge and the strings and take the post out and do measurements involving all 4 of those points. And it's all the things. You tap with the hammer at each one of the points and measure the response at all 4 of them. So that's 16 measurements. It's rather a laborious thing. I've only done it once. But the only doing it once was surprisingly successful. So this is, I'm glossing over the details here. It's quite laborious to measure these 16 admittances at the post ends and the bridge feet. And then we can use the soundpost model that I've talked about here and the bridge model that I talked about in the previous talk, and we can fit all of those. And here's the result. This is the frequency response to radiated sound from tapping at the bridge. The blue one is the measured response on the real thing. The red curve is my prediction of exactly the same sound radiation, but based entirely on these set of measurements on the box with no post and no bridge. So the empty corpus. And I've measured the mechanical response, the admittances, and also the sound radiation from each of those 4 places. And that has allowed me to put together this prediction of the radiated sound. And I was amazed how well this worked. It's not perfect, but it's pretty good. Now, finally, I can reveal something that goes right back to the beginning of the talk. Having seen that this looks as if it's working quite well for this virtual fitting, now in the computer, there is no problem in predicting the effect, the same sound radiation effect from having no post there. In the computer, nothing collapses from the force of the strings because I'm only using measurements that haven't got the bridge and the strings and the post. So this is actually the plot that I showed at the beginning when I said, here's the effect of removing a sound post. So it's a synthesized curve. The red curve with the post is the same as the red curve over here. The green curve is the result of running exactly the same prediction, simply setting that contact stiffness to 0. So the post might as well not be there. And it's very reassuring. That produces this effect that is now familiar. This is the tinny sound of a violin with no post. Right, so a little bit of summing up. what should you take home from this? The most important thing, perhaps because maybe you've never thought about this before, is that the behavior of the soundpost depends on these contact stiffnesses at the ends, which depends on how accurate your fit is, but also what the surface finish of the plates and of the ends of the post are. The axial stiffness seems to be way more important than the bending stiffness. That's good. That gives us a useful simplification. This leads to this sensitive effect of a small tilting of the post. And I think that's probably what goes to the essence of this position fit thing. Making a small shift to one end of the post may make a surprisingly large effect, may have the effect of a much bigger shift in the post because of this effect of the contact stiffness being bigger on one side or the other in a way that you can't guess and you can't see by looking at it. The tighter the post, the bigger those contact stiffnesses are, and potentially the more sensitive it might be to this kind of thing. So the tightness and the fit both influence these contact stiffnesses. The contact stiffnesses are what you need in a physics model. Now, the simplified model, this was the cigar box, suggests that east-west movement of the post may be more significantly more sensitive than north-south movement, and certainly gives a different effect. Now, I wouldn't want to read anything into the details of that cigar box model because it's not a real violin, but qualitatively, this may be true. I mean, the difference, because east-west, you're keeping the same distance to the bridge, but moving away in both directions from the center of the bridge foot. North-south movement, you're changing the distance to the bridge foot. And maybe that's really what's causing this effect. And finally, I did manage just once to do a complete virtual setup. And that worked, say, way better than I'd expected. And it does suggest that the models for the bridge from the last talk and the soundpost work well enough that, that we're on safe ground by deducing things from that. I only played a very limited number of sound demos here. If you would like to hear sound demos of those post-shift experiments in the cigar box violin, you can find them all in Euphonics. If you go to Euphonics and find section 7.6, you can read a differently worded version of this story and hear more examples. And with that, I think I'm done. Thank you.
All right. Thank you very much, Jim. Questions? Joseph, you want to, maybe it would be good if you moderated the questions and answers.
Sure. Well, first let me say how grateful I am to Jim, and I think we all should be in doing this work. You know, there's been research about all sorts of things in violin making, but really nothing about the post. And so my thinking always came to a dead end about what's important. And of course, when you can't think through it, then all sorts of wild ideas tend to proliferate, and there's certainly plenty of those around the violin world. Recipes for how to adjust, pushing it this way does this to violins in general. And so now that we've gotten to this, at least we can start, I think, making, designing experiments to test how it relates to our violin making practice. And we'll deal with that next month as far as we've gotten. But, well, okay, let me throw it open. I have some questions for Jim, but first let's, anyone else have questions? Hands up. Can you see, Fan, if anyone's got their hand up?
No, nobody has their hands up yet. Oh, no.
Oh,
Okay,
okay. David.
David.
It's physics rather than violins. Can you hear me? Because I'm
Yes.
Yeah,
noisy
Yes.
place.
sure.
You emphasize that the stiffness in question, it comes from surface roughness, but I presume that the spruce has a springiness this way
Yeah,
in the plate of the
yeah.
itself, and likewise. So is this something you could measure with engineering stuff about a static measurement of squeezing?
Uh, you've just reminded me of something I meant to say. Then I'll come back to your actual question. I should have said, well, when I talked about post resonances between rigid walls, I did that deliberately because that's a rather neat thing. Between the rather bendy, flexible walls of a real violin body, which it is by no means rigid, and so that means that the contact stiffness you need to have a post which might as well have been glued in is nowhere near as high as it would need to be if you're between rigid walls. So the range over which the contact stiffness matters is smaller because of the bendiness of the plates that you alluded to. And I meant to say that and I didn't. Could you measure the contact stiffness? Is that was your question? Not easily. I think my indirect deduction by fitting something is probably more reliable than any direct measurement. The trouble is that it depends on all the details of the not only of the actual surface finish of the top and the end of the post, but whether there is a tiny tilt or not and how tight the post has been wedged in. So you'd have to do the measurement on the actual violin without interfering with anything. And to measure the squashiness across the interface, you'd have to measure the motion on the top of the post and on the top plate or the back plate.
So it's not something that you would get from two small discs, spruce and whatever your post is made.
There will always be a contact stiffness, but it's dependent on the knife marks that you've left and how tight you've wedged it in and so on. So it varies with all the things.
I don't know that. You know that. Having measured little discs with different.
Yeah, that has probably been done, but I had an indirect measurement of that with my loose post and tighter post, and going through my indirect procedure where there was a factor of 3 in the contact stiffness with a tighter post and a looser post. An indirect measurement, but it all seemed to work fairly well, and it gave the answer I was expecting, so that must be right. Have people done this? Yeah, almost certainly they have. I mean, this is, let's say, where is the guy that I was mentioning when we were chatting at the beginning? This ex-colleague called Ken Johnson wrote this definitive book called Contact Mechanics, which is our Bible of this sort of thing. I suspect if I looked carefully in there would be measurements, probably not of wood, but the principle of contact stiffness, it's important in all kinds of things. It's important in how rolling mills work and all sorts of things. The metal contacts are what most of the research has been done on, but we've just got rough surfaces than your typical machined metal surface. So I don't know whether it's been specifically done on wood. It's possible in principle, but I quite like my indirect measurement.
So Joe will have seen or will see enormous variety between things that to the naked eye are almost the same. Right? I mean,
Well, that's enormous is a tricky word there, but you ask anyone who does set up for a living will have it as an article of faith that tiny adjustments to soundposts are fantastically important and fantastically expensive. And
fair enough, but I didn't know it depended on using 2000 grit or 4000 grit
yeah,
on the end of the post.
that's part of it, or at least that's where the tightness comes in. So it actually doesn't matter too much if you've actually got smoother surfaces, then I guess it would not need to be fitted so tightly to have a high contact stiffness. If your surfaces are a little rougher, if you wedge it in tight enough, you can always squash things down and get back to the same place. So there is an interplay between what the maker does and how tight you fit the post. There's only one parameter and it's influenced by all sorts of things. So to some extent, you can get to the same place in a number of different ways. And that might be interesting. And it does suggest things about some posts might be more sensitive to tightness than others, for example, which is up for grabs.
And we should remember that the longitudinal direction of the grain in the spruce makes it much stiffer than the top it's in contact with. So really we have a rigid thing on a mattress more than a springy thing going into a rigid thing, which looking at the model suggests.
Yeah. So Joseph, I think since we're on that topic, I think we should address, I think Andrew Ryan's point, which I think there's a misconception on his part about. So he's saying the sound post of a violin will always eventually fit and come to the same tension because the plates are flexible and not rigid. And then he says, so I think the misconception, well, let Jim address his comments are in the chat, Jim.
Yeah, now you've said it. I mean, it's a thing that Joseph always says as well. So must be true, mustn't it? Everyone agrees. Posts always fit after a while. I guess that's right. But once you're thinking of these rough surface asperities in there, what is going on? The posts only fit if some permanent squashing takes place, and that will have the effect of making the post a bit looser. And surely that agrees with what everyone knows, which is that after a while you need to fit a longer sound post once things have shaken down a little. This may be part of the process that's creating that. So that there is only one parameter, this stiffness. It's influenced by all sorts of different things, both woodworky things and time things as the things change, and how tight you put the post. But you're only you're manipulating one parameter in a number of different ways. So it's quite likely that you can get to the same place in different ways, or you can have a similar problem, acoustical issue, for what appear to be quite different reasons, because two different things that reduce the stiffness may have a similar effect.
We should let Anders, I think he was next. Let me just say though, to do with this thing of the post eventually fits, and so it's looser, as Jim says, but I think maybe what Andrew was getting at, the string tension is always the same, so it's just going to distort the top down, so you'll have some sort of a static load in the end that is the same. perhaps. But of course, there's so many other things going on in the meantime that I don't know, think that's a useful.
That's right. And who's done measurements? I mean, in principle, you could measure that by measuring this admittance on the top, right over the top of the post. And it will be really rather interesting to measure that with a newly set up instrument, and then every week for the first few years, you know. But no one has done that test.
We need a VSA grant to get one maker to get one violin and put it in a room, measure it every day with steel strings so that they aren't stretching. I think it would be a great experiment.
But it's this talk was aimed at physics and giving you things to think about. It absolutely there is no claim that I've said the last word in workshop practice to do with posts. That's your job.
Indeed. Anders?
Yeah, I was wondering about the string pressure. Does the string pressure make enough difference to the box to change the sound? I know that the shape of the body will change with the pressure, and it will change with humidity changes and so on, but only the string pressure should increase the pressure on the sound post in some way.
Yes. In terms of what I talked about with my virtual post fitting, the effect of the pressure on the sound post is dealt with by my procedure. And the string pressure will have other influences on the shape of the body. And the fact that this virtual fitting using this really simple soundpost model worked pretty well suggests to me that those other things are secondary. But there will certainly be an effect on the ends of the post, which will just be one of these several factors that influences the effective contact stiffness. I think contact stiffness is the thing to think about, and it's you're influencing that by several different routes, including the strings.
So is the contact stiffness much different from the wood stiffness itself in that direction?
It's lower. But once you have to think carefully what you mean, because the units are different. But it's but that's what's leading the if the stiffness gets high enough, then the post might as well be glued into place. So that's the ultimately, you know.
And some put drops of glue on the top, maybe. I don't know what's the practice, but it's easy to put a super glue drop on both the sound post and the top plate. That would make changes to the contact stiffness, I guess.
It would make it really difficult to shift the post or get it out next time.
No, because you let it dry before you put it in. So
okay. I just a kind of hardening effect. Yeah, that's possible. I mean, filling and smoothing it off again. I guess that would all be part of what the surface topography. But certainly the stiffness of the material as well as the topography is what governs these. This
Anders, that experiment is a little more complicated than it seems, because the super glue itself has a certain squashiness. It's not.
Yes, I know that. I know that.
Yeah.
Okay. Let's let Jay ask his question.
No, it's just I found it a little interesting that if you've got the post and you push it toward the bass bar side just a little bit, so you create a tilt in it, let's say 1 millimeter. It was interesting that you had said that, you know, at least until things distort, you actually have effectively moved the because of the wedge shape, you've actually moved the effective contact of the sound post to the top over to maybe 2 or 3 millimeters. So you think you moved it to the west, but you've actually effectively moved it to the east. which was kind of a
Yeah,
strange
well,
phenomenon.
you've moved it east on the top and west on the back, if you've
Yeah.
tilted it, I
Yes.
suppose, or the converse. Yeah, that's my mental image.
Yeah.
Um, Anders, did you still have your hand up, or I guess not.
Sorry. I have one comment only, and that is when we put in the soundpost, we put it in with the grain lines going parallel to the bridge, and the wood in the top is going longitudinal with the body of the instrument. So the main contact should be between the hard parts of the wood in the top and in the soundpost. So it's a grid, more or less.
Yeah, that
Agreed.
sounds right to me. Yes.
Mhm.
Yeah.
Okay. But before I Jeffrey asked, could I just run by one image? I had a lot of trouble getting an intuitive sense of this contact stiffness and thinking of a spring, because the spring is so short. I mean, it's tiny fraction of a millimeter where those asperities are, isn't it, Jim? I mean, we're talking about very small
Yeah.
bumps. So let's say we imagine that the post was glued at the top and the back, and that we were varying and we think of the post itself as a spring and just turn the knob for stiffness in that. In your model, that would have the same effect as the contact stiffness at the end?
No. I might have to think about that. So, I mean, it's in there in the model, certainly, and it will contribute to it. Okay. Yes. But it's not something that varies sensitively. The axial stiffness of the post won't do any of these interesting things to do with small tilts and so on. It just these. I think these asperity effects. Well, I thought of the idea, so I think it's a really good idea.
Oh, I think, I mean, almost everything you say is correct, because you know what you're talking about. How it applies to what we do is a guess, and we've got to fill in those blanks. Jeffrey.
Since we were talking some about positioning, is it not totally common practice to adjust the stiffness of the tightness of the fit by just kicking the bottom of the post slightly in or out without moving the top? I mean, I find that the physical distance or the relationship of the top has more of an instant effect than the back does. Plus, my second question is, does anyone have any experience with these, I guess they're pretty new, mechanical sound posts that you can adjust the tension with by what you were just saying, Joseph, that if you had a little knob in the middle to lengthen it, that would adjust the length. And I gather that those artificial mechanical sound posts also have little adjustable pads at the end to control the fit. Has anyone had an experience with those?
Yes. I've done quite a bit over the years with that. And for the month before the Oberlin experiment, we spent a lot of time in the shop designing those and looking at what works and doesn't, and came up with a very easy to make one that does work very well. And we'll be showing that next month. And if well, we'll talk more about it next month. To do with your first question, well, Jim can answer, but I think he would say what you're doing is something else. I mean, it's going to do something, but it's not a precise equivalent of changing the length of the post, at least in the physics model. Is that right, Jim?
Yeah, certainly. If you've got a post with tilting ends so that it appears to conform all the time, you lose this degree of freedom to do with thing you said, shoving the bottom in and tilting it, because it will thwart you when you try to do. I mean, I would expect those posts to behave differently than what you're used to with a regular wood post, perhaps because, I mean, there are other reasons, but because of this mechanism. But I do suspect that, as Geoffrey said at the beginning, the natural way to make a post feel tighter is actually to push the bottom of it and to tilt it a little. And it may be, if that's what people are talking about when they say tightness is the most important thing, then they are doing a surprisingly big position shift as well when they do that adjustment, because you might be moving you might be moving up to 3 millimeters or something in the effective position of the top of the post by doing that, even though it doesn't look as if it's moved at all.
Well, I think what I would do and would be, an instrument comes back, you do that, it sounds better. Okay, take the post out, put a longer one in, and you will gain that same advantage typically, which suggests to me that the position on the back isn't nearly as important as the position on the front. So if we just keep the position on the front changed, we're effectively doing that.
I'm sure you're right there, but the position on the front is not such a precise thing as you might think. Once you start saying that the effective position is not right in the middle of the footprint necessarily, because if you've got a small tilt, it's towards one edge or the other, and if you've got a 5 millimeter post, you're moving a couple of millimeters all around inside that footprint potentially. And maybe that's what people are hearing. Well, that's part of what people are hearing when they describe these sensitive effects.
Of course, I'm talking about cellos, and the surface areas are much greater. I mean, it would seem that I don't know whether all the effects are exactly the same between violins and cellos, even though the principles seem like they would.
The principle is that I got the remark from Robin Aitchison, who was, of course, also talking about cellos. So as far as it goes, yeah, I don't know if Robin is here today, but yeah.
Andreas.
Hi, Jim. First, thanks a lot for your talk. I still have some misgivings. I think we're missing something. Well, the easiest way to formulate those, I feel you basically you're saying a tight post is ultimately like the ends are glued in, and me imagining having a moderately a normal tight post, and I'm filling in the ends with glue. Instinctively, I absolutely don't think this will sound anything like a really tight post. If I can deaden a violin, if I make a really tight post, it can be completely dead. Whereas if I imagine having a normal or loose post with glue at the ends, clearly this is my instinctive reaction, but a lot of what I'm doing is like that. I just don't think that by having taken away those springs or hardened those, I will have the same effect as if I'm pushing both plates out. I think something else must be happening on both plates, that their vibration is changing if they are pushed very hard in a direction. And I can't explain what it is. It's just, I still think there is an extra effect that so far we haven't been describing.
I'm perfectly happy to believe that the world is full of things that are not in this model, for sure. Now, what do you mean by deaden? Or more to the point, if you can create this effect on demand, then you should bring an instrument to Cambridge sometime and deaden it and undeaden it, and we'll do some measurements and try to find out what deaden means.
I guess that's a good suggestion. You should do that.
Well, I think you're making a good point, and I've struggled with the same question. You've got these little tiny springs, which Jim is changing his knob to stiffen. So you can stiffen them by essentially filling in, making it flat, or you can stiffen them by pressing down. But if you press up on the top, you're changing the arching. So you put a higher and higher post, you're changing the arching, which will have an effect unrelated to the post. So I mean, that's why we make posts that fit. So we don't have to we don't have to do that.
Yeah, but then some people still put longer and longer posts in and distort arching, as is well known. What are they trying to do when they do that?
I think they're chasing high frequencies, and I think you get a temporary fix, and then the plate settles into the new position, and that's why with a lot of the old instruments you can look right through the F-holes from the side because they've been pushed up so high. But that's I guess speculating. But I think it's been shown that tension, the force down on a plate makes surprisingly little difference. Remember, we did the talks about measuring with and without string tension. It makes really very little difference. If we saw big differences doing that, then we wouldn't be surprised that lengthening the soundposts made big differences. But I think we don't, and I think as Jim showed, it doesn't make such a difference. But Jim, if I have you right, as long as it's tight enough to have a good nominal fit, whatever that is, you don't need it any tighter, or you don't need it any stiffer.
There is certainly a limit where once you get near that, then making it stiffer doesn't make any difference. Whether you can recognize what that is, because if you've got really hardened, smooth surfaces which fit perfectly, and then someone does a tiny tilt to the bottom, then actually you have a more drastic effect than you had before, because you will actually open up a gap with a smaller tilt than you needed when there was a bit of give in the ends. So
let's look at the chats. Do we have is there anything from the chats that we haven't addressed? I see things like asperities are meaningless.
Well, I think part of the thing is I think a lot of us are having find it difficult mentally to understand this model, of this contact stiffness and how it fits into the larger scheme of things. And yeah, I think that's one of the initial hurdles is that.
And the thing you can do if you want to convince yourself that there is an effect is take a length of soundpost with nice flat square ends and put it in a vise and then tighten it up and tap it on the side and listen to the frequency, because the theory, if your ends are essentially fixed, then increasing the tension in the post will make the frequency go down. It's like it's the opposite of tension in a string. You're putting compression in it. Tension makes frequencies go up, compression makes frequencies go down. You do the experiment with a post in a vise and you tap it, and what you hear is the frequencies going up. So it actually moves in the opposite direction. And the reason for that is because you're making these contact stiffnesses higher. So that is a simple workshop way of convincing yourself that there's something going on here. How much it matters and whether, all of these things so that's with rigid ends in a vice. But that was the thing I did first, and I was expecting the frequency to go down, and it went up. That was what made me see that contact stiffnesses are doing something, at least in that context where you put something in a vice. It's a very striking effect, because say
post
the
and the
frequencies
vice-
actually move.
The frequency you hear aren't those are the transverse vibrations.
Bending frequencies are the
Bending.
easiest ones to hear. Yeah,
That's
yeah.
what you hear.
So they depend on these
but-
torsion springs, but they all
since
scale
it's a
with the
solid, we need a real engineer to tell us what happens when we squeeze this way to that stiffness.
Yeah, but
Not you are.
the bending resonance is, I mean, the torsion springs and the axial springs are governed by the same thing.
Yeah, no, I got that.
It's just
But
a
what I'm
different
saying is,
average, and
it's
it's easier to hear the transverse modes.
Those are the ones that go up. That's what you hear. And because
Yeah.
it's a three-dimensional solid, it's above my pay grade to know what happens when I compress it longitudinally to that bending stiffness.
It's
And isn't there an answer to that just in the bulk that has nothing to do with the ends?
Didn't Jim just
When you
explain it,
derive
there's
the
general-
bending stiffness or the whatever the effective one-dimensional equation of motion for waves, for transverse waves.
Yeah.
When you derive that from a three-dimensional object with its stress tensor, you do all kinds of things. And now if I don't know how it changes. Is
Yeah.
there a bulk answer, which is what?
Yeah, maybe we could have an offline. There's a contribution from the bulk, but they certainly say it's easiest to think about the transverse modes. The fact that the frequency varies in the opposite direction to what the simple equation says is, and I think contact stiffness is the only effect that creates that.
It's hard to believe.
Yeah.
Anders?
Strange but true.
Yeah. I wonder, it's a simple way to deal with the fitting is to make the top and the lower part of the sound post a little bit round shaped. And I guess that's not a good idea if you want to have a good sound.
Why would that help with fit?
Because it's easier. You will always have a fit. But it might be a little bit pointy.
It'll make a dent in the top, presumably.
Yes, a little bit. Yes, you will see. You might see it on the top. Yeah.
So then I guess your post would then click into place if you have to stand it up again, as long as you wanted it in the same place. Yeah.
Yeah. But I have another question. I understand that this was a stupid idea, but another thing to do when you fit something is to use chalk. And fit with chalk, and it also increases the what is it called? It will be more steady or better
friction.
Friction, yes.
Yeah.
What will happen? What is that a good or a bad idea to use chalk?
Like fitting dentures.
Sorry?
I said like fitting dentures in your mouth, with denture.
Yeah, yes.
Bite down, please.
Yeah.
But now we're squarely in workshop practice.
Yes. Quite
it's,
so.
I'm just looking at the. Okay, Raymond Shire asks, can your scope of experiments include different densities of post? Next month we'll talk about. We did try a bunch of changing post materials, changing the mass of the post, and we'll have some results for those. Let me see who else. Andy, you were one of the most skeptical in the comments. Have we convinced you, or Andrew Rand, or are you still shaking your head? So what's the kernel of your dissatisfaction with this theory.
So fit, if your post doesn't fit, it will eventually fit. So it is not a stable measurement. How can you adjust a violin to sound its best with something that will change over time? Meaning, if that misfit is important to how it's sounding, is the thing that's making it sound, it's going to deteriorate over time. And there are plenty of instruments I know that you set the post in the right place once, 25 years later, it's in the right place. If you don't mess around with the violin, it just sounds good. Yes, it changes with the variables that a piece of wood undergoes, from humidity, from travel, from all these things, but it remains constantly itself. So fit, tension, you're always going to chase tension. It's, as you said, that you put a tighter post in, you come back a month, just as Jim said, he took the sound post down on the violin that he was measuring, he found it was too loose, or looser than he'd like, because you can't, tension is unstable. It will, if you put a tighter post in, you come back 6 months later and it's loose. Then you put a tight post in again, you come back later, it's loose again. They're flexible plates. They are never going to be stable. They will, until they reach their inelasticity, which is some, I don't know where that is on a violin, till it becomes a decahedron. I don't know. It's like the post has pushed everything out to a tent shape. So we fit the post properly, so that it is stable. The fit fits the top. We do it for conservation of the instrument, not for tonal reasons. We fit it so that it is a correct connection and will not deform the plates. We make the tension of a suitable amount, and that changes different instruments. Some instruments are more flexible, some are less flexible when you put it under load, so that the post is long enough to maintain the shape of the instrument under load, to have a sort of minimum tension, or I don't know the technical term, that it is sufficiently tight when the instrument is brought up to tension. Any more than that, we don't need. Less than that is inefficient. But that's all. You just have to have sufficient firmness of the post within the box to accommodate that. It's not about sound for me. It's just the tension is not about the sound. Other than if there's too little tension, it's not going to sound its best. If it's too much, come back to 6 months later and it will probably be okay. Or even 6 months for it be too loose. The box will conform to whatever the length of the sound post is. The arch will deform. So we make the tension correct so the arch does not form. We fit the post properly so the arch does not deform. As far as this contact, I mean, if you look at old plates, they're often super smooth. The wood is so compressed, so smooth there. I can't imagine these asperities have any meaning to the sound at all. They just can't, their influence cannot be of any significance to me. I just fail to see how they can make the difference in any meaningful way. Yes, you probably can measure the difference, but to me, it's not the important thing. I think if you go...
It sounds as if you're not someone who makes your living as a tone adjuster. I mean, I got these.
I make violins, so I'm always tone adjusting.
But say Robin Aitchison was my source of information on some of these things.
I spent almost 20 years as a foreman of the Rooney & Son violin shop. I've adjusted thousands and thousands of violins. I've put thousands and thousands of violin posts.
I wasn't criticizing that.
No, I'm just giving you my background. I was
interested in your remark that it's not about sound. I
The
hear some people saying that post adjustment
post adjustment is super critical. Super critical for sound. Yeah.
Okay.
Fit.
Why?
Why? Because it makes the box behave in an efficient way. If that, we won't. That's a huge discussion, but we'll just say that just as you said in the beginning. Okay, if you put a sound post in the middle of the violin, or you didn't have a sound post, you have a certain output.
Yeah.
Initially, then you put a sound post in that's asymmetrical. The sound changes dramatically because the instrument functions differently. If you measure the difference between the violin box without the sound post and the violin box with the sound post, you also see changes in frequency of the structure. So having the post in there, I think for me, the position is the most important. The position is the thing that will allow the instrument to function properly. I don't want to extend this into what that means, but the fit, we only do the fit so that we conserve the plates, and the tension is they are technical. You have to meet the threshold of that they don't deform the instrument. If they don't fit well, yes, it will deteriorate the sound. If the tension is incorrect, it will deteriorate the sound. But we don't do those two things principally for the sound. We do them to preserve the instrument. That's principally their function. A good fit, a good tension that's just a minimum standard of how how the sound post functions. Now, when you find the place where the sound post should go, then you should refit it and make sure the tension is correct. Again, to preserve the sound. Now, if you're adjusting an instrument and you get these gaps and things like that, yes, they can change the sound. I'm not denying that. A little bit like you were saying, if it's dramatically different, it can change the apparent position of the sound post because its contact point is not in the center of the post anymore. It's at the edge. So effectively, the post is in a different position than you think it is in. But position for me is the crux of the matter. So talks about gaps or asperities or things, I think just completely is small potatoes. Sorry.
Well,
I'm sorry to drop a hand grenade in the conversation, but
well, not at all. I mean, it's like the blow up in your hand if you really want to
if I held
hold
on
it, if you really want to hold onto it. I generally agree with you when I think when Jim first told me of the hierarchy of things, I said I don't consider fit an option. I mean, it's got to fit. I mean, and I think most violin makers feel that way. But when you say that, you speak as though there's wide agreement in our profession. Unfortunately, there isn't. How many times have you put a perfectly fitted post on your violin? Some other maker gets hold of it, and it's all over the place. And it makes a difference to sound. And Jim is certainly pointing out just some of the reasons it might make a difference to sound. Whether you consider that small potatoes or not is something else.
I agree. But I would say if the post doesn't fit, then you can't really adjust it because you don't know where the post is. It's not functioning the way it's supposed to function. I would say that. Or if the tension is not correct, meaning sufficient to fill up the arch and not so much.
Andrew, can you define what do you mean by it fits well? What is how do you define fits well?
The two surfaces meet perfectly. Yeah, that's a fit. And you can, I mean, if you're fitting a post, you can see when it fits well. When you take it out, the post will bear the marks of the plate on it that it is making contact equally across its surface. I mean, the two parts just have to fit together. And if it's an old violin, that can be difficult because often there's a lot of distortions in the plates and things like that. New instruments, it's easier, but they have to meet perfectly with each other. I would say the tool of choice would be a sharp edged instrument to cut it with. So I wouldn't fit it with a file. I would fit it with a knife or a chisel so that the surface itself is smooth. I mean, I would call that a smooth surface, something that's cut with a cutting tool. I would say that is not a rough surface. I would say
But
that.
it is once you look under the microscope, of course, because it's still got wood cells in there.
Yeah,
But
but
we're talking about microns.
I can tell you that there are great sounding violins that have soundposts fit with cutting tools, and that is sufficient. That is sufficient.
Oh yeah, sure. I know. I don't doubt that. But everything is rough if you look hard enough, is all I was saying.
Right.
Well, although I don't think there are makers who believe, or I haven't heard it proposed, that one tonal adjustment is taking a fitting post and cutting some chunks out of it. I mean, effectively that happens, but I don't think anyone thinks that's a good idea. So
Right.
I don't think we should get too exercised about that. But it is interesting to know, if you're curious about these things, what the effects of these things would be as one element. And Jim is addressing that, but also position. Yeah, of course. It isn't so obvious to me that the length of the post doesn't make much difference. And I think, well, I think we'll see next month that experimentally it didn't make so much difference compared with position. So I do think it points to position being the king, everything else being well handled. Well, Jeffrey, what are you thinking?
I'm thinking back to, I guess it was the 80s when Rene Morel was the god in New York for New York musicians getting their instruments adjusted. And he was famous for pulling soundposts way out beyond the bridge foot in many, many cases on violins and on cellos. Now, I'm not sure whether that was mostly taking the existing soundpost and pulling it out for tightness, or fitting a new soundpost and making sure that he pulled it way out. But he felt that that produced the sound that New York string players were looking for, which was supercharged and hot.
So the problem with that, understanding that situation, is when you move the posts, you've changed its position and its tension. So how can you disentangle those two as to what the effect is on the sound?
Of course, I'm aware of that.
So I'm speaking here more as
Right.
So as violin makers, your experiment would have to be, okay, let's fit a post that's in that new position, that's at the proper tension, not tight, or that's fit a post that's tighter in the old position. Is it a tension thing or is it a position change? And
we did do experiments with doing exactly that, tilting the post one way or the other. I remember the first one we did at the shop here, Luke and I, because Jim was bringing this up. We had a post well fitted. We pushed the bottom of the post upwards. It made a difference, and what looked to me like a positive difference. Then we pushed it the same amount in the opposite direction. It also made what looked like a positive direction.
When you say upwards, do you mean north on the bottom?
I'm saying towards the ribs.
Oh, okay.
Yeah.
That's what Morel would do.
Right.
So we're never going to find a unique solution to this. It's not going to be, because everything remains as it is. As a machinist friend of mine used to say, the universe is made out of jelly. Everything's moving around, and Jim's not doing fluid dynamics here. But anyway, David.
If
Thank you.
someone wants to experiment with compliance at the end of the soundposts, what I did one time was I took sheets of various thicknesses of rubber and cut out little doilies for the soundpost and glued them on. Now with the rubber on the end, the end will be much more compliant, but you can't really move it around, it sticks. So then you glue a little piece of paper on the outside of that. So you made a sandwich, a rubber sandwich. And it's kind of interesting to try those in an instrument and see how it changes the sound.
How did it?
Yeah, and then you actually have an audible difference. You know, it's not something you're looking at it on a graph or something. You can actually hear differences.
But what was the difference?
I would say I only tried it on 2 instruments. They were both violas, and I would say generally sort of what you'd expect. They lost focus and got fuzzy.
Rubberier.
So it's sort of the opposite of a Rennie sound adjustment.
Yeah, but those were violas, so maybe that was a good thing.
Yeah, usually.
Interesting. And so that would be really, in Jim's model, you're changing the contact stiffness. Is that right, Jim?
Yeah.
Or is it?
Yeah. It would have the same, absolutely have the same effect. No, it's a natural way. I mean, it's an interesting way to explore that in a different way.
Yeah, and see how it affects the sound and the feel. To me, the feedback a player gets from the instrument is very important. The physical feedback, not just the audible feedback.
Mm-hmm. Andreas?
Now, we've touched, or somebody touched on the adjustable carbon fiber soundposts earlier. Now, just since they've got swivel ends, I would say independent of the length that's adjustable, I would have said the fit is basically in fairly good because it swivels into its best position and it won't change so much. Would you agree that, you know, but we're still getting quite large tonal differences with the adjustment of the length of those soundposts? Would you say it's just a compression and still a fit issue that we're seeing, Jim?
Well, I don't know, but one thing to point out is that if you've got a ball and socket swivel, that's another pair of surfaces which will have a contact stiffness.
I've given that some thought. I mean, obviously I haven't measured any of those, but I would have thought that within the vibrations of an instrument that basically the sockets are stiff enough not to move under that pressure. I mean, I might be wrong. Just intuitively, that's what I would think. I don't think they swivel while we're playing. Suppose it's something to be confirmed or disproven.
Well, it's exactly what I worry about. If you have a ball and socket, it fits. But if the plate is doing that, is the ball going with it or is it constraining it? I mean, what is the friction of the ball against the inside? Is it frequency dependent? I mean, I imagine you could put sensors in there and answer that question.
Mm-hmm. Just earlier, Jim, you mentioned the experiment of the soundpost in the vise, and if I understood it right, you were expecting with increasing tension the frequencies to go down, and they went up. Is that correct?
Yeah.
So what if you repeated that? I mean, just to confirm that, you haven't by any chance tried then putting a drop of super glue at the ends and do the same thing? Basically sort of connecting the ends?
It could be done. I haven't tried it. I
mean,
it was a rather quick thing. But
I'm just sort of looking where else. I'm intuitively, I'm still struggling that all the effects can be down to it kind of, connecting fully or not. And
yeah,
that
I mean, that
doesn't quite
particular
sit right.
experiment, that particular experiment is very clean. Nothing to do with violins and sound. It just does a frequency go up or down. The fact that it goes in the opposite direction than all the textbooks say is very revealing. Yes, it could be tried with glue. Everything has some stiffness. I don't know what the answer would that be. It was just a vice, so I wasn't. I didn't try gluing the soundpost into my vice first. Could be done.
Jeffrey, is your hand still up or?
Yes,
Yeah,
it
go ahead.
is. This is regarding both Andreas and Joseph's brief discussion there about the carbon fiber soundpost. What I'm holding here is a stand for a camera for a computer, and it has a ball and socket joint that has a little tension adjuster, so I can loosen the screw, adjust the top, and then tighten the screw, which locks the ball into the socket. I mean, I suppose that's an additional complication, but one could have a little tightening adjuster like that on a carbon fiber sound post. So once you got the top and bottom exactly the way you want them, you could then tighten it so there would be no chance of it moving. And kind of related to that, does anyone know the name of Alfio Batelli, a maker originally from Florence that worked in Los Angeles in the 50s, 60s, and 70s and was kind of the go-to guy for members of the LA Philharmonic? He would always, when you went to see him, he would ask you if he wanted you to cut, if you wanted him to cut a hatch in the C-bout of your cello so you could just reach in and adjust the sound post. And of course, he was being humorous, but I was wondering if one is doing research on sound posts. Of course, that one would first have to do the experiment to see with whatever cello you're experimenting with, obviously not a really good one, that what would happen to the sound and the fit of the sound post if you had essentially a little window in the C-bout. But if you could, I mean, if things would stay kind of the same, you would obviously make it as small as possible. But to do experiments with a sound post, to be able to just reach in, pull it out, do what you want and change it without having to go through the F-hole and all that complication, it would seem to be a very interesting experiment.
Well, I think one advantage of the F-hole is it keeps a lot of people out of there who shouldn't be in.
Oh, I've
in there.
seen people who have become addicted to it.
Oh yeah.
I was backstage about to go on stage with a very well-known violinist, and he was in his practice room next to mine, and all of a sudden I heard a string of curses because 5 minutes before walking on stage, he had just knocked down his sound post.
Well, the great virtuoso Rogero Ricci used to adjust his sound post with a kitchen knife, tapping it around, and that he shredded the inside of the Del Gesù. I mean, people do these things.
I once adjusted a sound post in Alaska with string because someone's sound post had fallen down, and I, had a loop around the top and the bottom, fed it through the F-holes and managed to get it kind of in the right place. So when I put on the tension, it stayed there. I mean, it's, you're in the middle of the bush, as they call it in Alaska. That's what you got.
Very good. Evan, can you straighten us out?
Well, I want to go back to Jim Woodhouse's clamping rig, because there's two things going on there. In one case, you are setting the boundary condition as you apply some force onto the system, but you're also putting a preload in. So in any column, when you're building things, you put enough preload in it, the system will buckle, which is basically driving the frequency down to 0 hertz. So you have the boundary condition phenomena happening, plus you have the preload condition happening. So the preload will actually drive you down to zero frequency with enough preload on it. So you have to be careful that you got those two different phenomena going in there.
That's
Very true.
certainly true. Yeah, no,
Yeah.
that's what I was expecting. You know, yeah, and you're moving from a hinged to a clamped
When the
boundary
frequency
condition
goes up there.
as you make the end stiffer. But I was surprised that within a reasonable range of soundpost fitting pressures,
Yeah.
the boundary conditions always win.
Yeah, yeah. But if you keep applying that force in there, you can drive it down to zero.
Oh yes, yeah, absolutely.
Yeah.
That's no, that
I just wanted to articulate that to our audience. I wasn't trying to educate you.
no, buckling. No, that's, and I always tell civil engineers the whole of civil engineering structures is just the zero frequency
Right,
limit of
yeah.
vibration. And all that they make rather a song and dance about buckling, but it's buckling theory is all about driving a frequency down to zero. Absolutely.
I'm looking at the chat. You see Clarissa Petty says, I would disagree that it's a matter of finding it difficult to conceptualize. There is no substitute for a good ear and practical experiments with actual instruments. Unfortunately, or not, the perception of tone, how good or bad it is highly subjective and dependent on so many factors as to render strict scientific experiments such as this of little practical value, however intellectually interesting it might be. I realize no claim has been made as to the value of developing workshop practices, but in that case, what is the point? Okay, this is a point of view I certainly started out with as a young maker. I thought, why are these scientists getting their muddy footprints in our craft? They don't know anything about sound. I don't know. I'm putting my own original bias in there, but I do think it's important to separate, to not think that scientists are thinking they're trying to help you make better violins or worse violins. I think Jim has stressed this a lot. Do you want to take it up from there, Jim? Your job is something different than that.
Yeah, that's I watch what makers do and hear what they say and then try to make sense of it in what the physics is. Sometimes that like the bridge was an example where the thinking about the physics did in fact have some payoff that fed back into workshop practice, and that might be eventually true with these other things. But science, you go a step at a time and you put pieces in the jigsaw, and eventually you see more of the picture, which you wouldn't have known without all those people doing patient work. But it's not for everyone.
Agreed. Anders?
Yeah, I want to return to what Andreas was talking about with the drop of super glue. I don't know if everybody knows about this very thin, low friction super glue that you can buy from Stumac, and it's not sold in the normal workshops or boutiques. And I think if you put a drop of that on wood, it will penetrate the wood quite a lot, and you have something that is much stiffer. If you put it on a bridge, you can send the frequency of that bridge up several hundred hertz, maybe 1,000 hertz. So it becomes a very stiff system. So that's just what I want to say. I guess your son is a guitar maker. I'm sure he has super glue in his shop. And maybe something can be done. And when we talk about putting super glue on the soundpost, it is to put it on the soundpost and not glue in the soundpost, but to increase the stiffness of the ends, and then test it maybe.
Yeah.
There's certainly a lot of things one could try around the edges of this. It's uh, let me read another thing that's come in. Kevin Crow, please help me out. We are assuming that the post only affects the top plate. Is there not an interplay between the two plates that can be tuned by the stiffness and the position of the post? Jim?
I guess that was the thing I mean, the cigar box model has all that fully in a context where you can do it thoroughly. The virtual fitting in the real violin, that's the reason you have to measure on the topper and on the back at the post foot position. So that effect is factored into all the things I've been talking about.
Okay. And Andrea Ortona, what is the impact of mass? We'll did a little bit on that before Oberlin. It doesn't, and haven't finished. It doesn't seem to make a lot of difference, but that's still to be studied. If you do things like putting a little lump of modeling clay at each end of the post, you can hear differences. It seems to be slightly more sensitive at the top end, I think, suggesting that the post is also moving sideways rather than just up and down. I mean, or some of the there's some mode in the top which caused it to translate a little bit, but I don't think that do makers experiment by putting heavy posts or light posts? I don't know that that's a anyone want to pitch in on that? No.
Well, Joseph, all right. Joseph,
Mhm.
one of the comments about, using the carbon fiber adjustable sound posts were that they were, the mass was considerably greater than standard wood sound posts.
About 6 or 7 times, yeah.
Yeah, exactly. And that was an additional variable to certain experiments that we did. And I know some makers don't like them for that reason.
Yeah, I think if you're getting that much heavier, you expect to hear an effect. I mean, it's probably a slight muting. Usually that's what putting mass around the treble foot does. But I think that any normal density of spruce, you're going to see a range of a post might weigh half a gram, it might weigh 3/4, it might weigh a gram maybe, and I don't think that's going to make a big difference in the results. But I remember one violin, I actually drilled a hole in the post and put some lead weight in it because when I put it on the back right underneath the post, it seemed to help the sound. So I did do that. About a year later, the person had a buzz. And you can guess what it was. The mass was shaking around in the post. But, that's the thing about making, isn't it? There's so many weird little tricks we can do that'll solve one problem, at least for a while. It's hard to generalize from any of them or learn much, except, okay, you could try that.
Let me go back to Kevin's question about, the effect of the post and the tension on the box, because I think this addresses more of a general idea of the vibrational properties of, let's say, plates or a box in this case. How affected are they by certain boundary conditions, such as, a stiffening post, independent of the making it as asymmetrical. But if you add a stiffening member, inside it, how does that qualitatively affect the vibrational properties of the plates on the box?
A lot. I mean,
Yeah, which I think is what makers' perceptions is, but is there some guidance or pattern?
I'm sorry, could you say that again? To increasing the length of the post?
Well, the point is that there's a perception that changing the tension, let's say of a post or a stiffening member, inside the box will change the vibrational properties of the box, and that's why people are surprised. For example, when we claim that changing the downward force of the string tensions doesn't change it as anywhere near as much as people think they do.
yeah.
And how do you reconcile those two statements or observations?
My answer is to build models, and see what it does in the computer. I guess Colin did some of those things in his finite element stuff, but it depends. You'd need to firm up the question a bit to turn it into something that could be investigated cleanly.
Yeah, I found that if you look at individual workshop strategies, changing the bridge tuning, changing the post, changing the weight of the tops, you can do measurements, but there's always a spread in the measurements, repeatability and everything else, and from one thing to another. The usefulness of this kind of research is that you can say, overall, the differences I'm seeing averages out, so there's probably no direct link, or there's a trend this way or that, in which case it makes sense to try doing that again if the same problem comes up. But I think it's always going to be fuzzy. I don't see any way out of that. Anders?
Yeah, I was wondering about the cellos. If you have any thoughts about your ideas and measurements you've presented here. The cello bridge is a little bit different from the violin bridge. Do you think the results you have presented will transfer also to the cello? I think about the Hardanger fiddle, of course, but I'm asking about the cello because I know you know the cello very well.
Yeah, the soundpost model is no difference, but yeah, the cello bridge is certainly very different from a violin bridge. Different vibration modes. I talked a bit about that in the previous talk. It's you get a third body hill from the leg swaying resonance of the bridge. So there's another degree of freedom. Cello adjusters have an extra degree of freedom that violin adjusters don't have. No doubt they make use of it.
Of course, there's also French bridge versus Belgian bridge for cello.
Yeah. Yes, yeah.
But it doesn't strike me that a cello is further from a cigar box than a violin is. I mean, it's kind of
it's just a bigger cigar box.
Bigger cigar box.
Yeah. I guess your earlier talk on bridges is on YouTube.
Should be.
I think so.
Yeah.
Yes.
Yeah.
And when we have the site up, which will be a matter of probably 4 or 5 months, that'll also be a place where you can come and it'll continually update the talks and hopefully various ways of searching for them, so one doesn't have to scroll through pages on YouTube so much.
There's a bit about cello bridges in euphonics.
Yes.
One of my great antique store finds.
Nice.
Oh yeah. A real cigar box. Yeah.
Exactly.
Yeah.
All right. I think people are exhausted by the technical questions. Yeah. So thank you very much, Jim. again, and